the last lesson, I have introduced about the concept of stresses. In this particular lesson, we are going to look into some more aspects of analysis of stresses. Before we go into the details of the analysis, let us look into the questions which we had posed last time. The first question which was posed was, what are the units of force and stress? Well, these are given within the lesson itself, and I am sure all of you have got it. Unit of force is Newton and unit of stress is Newton per meter square or Pascal. This can be represented also in terms of megapascal or gigapascal. The second question was, what is the definition of normal stress? Well, it can be defined as stress acting normal to the plane as normal stress. In the last class, I had explained that if you have a body which is the free body from a major body and is acted on by forces, there will be resulting forces into it which will keep the body in equilibrium. Now, at a particular small element, if we take that this is the resulting stress, then we can decompose this stress into two components. One is along the normal direction of this particular cross section, which is this, and another component along the plane of this particular section. The component which is acting normal to this particular cross section is normally known as the normal stress. So, the normal stress is the normal component or perpendicular to the particular section. What is meant by free body diagram? Free body diagram is a diagram of a body as a whole which are acted on by external or resistive forces or a part of it. So, it can be a whole body acted on by active forces and resistive forces, or if we cut any section from the body and if they are acted on by the forces and the resistive forces which will keep the body in equilibrium, we call that as the free body diagram of that particular configuration. Let us say we have a body which is supported at these 2 points and acted on by forces. If we like to draw the free body diagram of it, let us say we draw the diagram subjected to the external forces. Now, is it the free body of this whole diagram? No, this is not the right diagram. The right diagram will be, if we take the body acted on by the active force, also at the support point you have the resistive forces which will keep the body in equilibrium, then this is the true free body diagram of this particular body. Now, supposing if we want to cut this body through a plane and separate it out in 2 halves, then we have this half which is acted on by active and resistive forces. Also, at this section we will have resistive forces generated which will keep this part of the whole body in equilibrium, then this particular part also is a free body of the whole structural form. So, free body diagram is essentially when they are acted on by the active force and the resistive forces of the whole body or part of a body which are subjected to the external active and resistive forces and the internal resistive forces. The last question was, what are the axioms on which behavior of deformable member subjected to forces depend? Well, here we have first thing, which is equilibrium of forces. The fundamental laws of Newtonian mechanics is used for the equilibrium of forces, and for this a body must be such that it must be having all the forces acting in the x direction. Summation of forces in the x direction should be equals to 0, summation of forces in y direction should be equals to 0, summation of forces in z direction should be 0. Also, the moment of all the forces taken about x, y or z axis or parallel to them should be equals to 0, or in effect we can say that summation of moment about x axis 0, summation of moment y equals to 0, summation of moment for z or parallel to z axis equals to 0. These equations must be satisfied, fulfilled for the body which is in space. In a two dimensional form, these equilibrium equations reduces to summation of forces in the x direction equals to 0, summation of forces in y direction equals to 0, and summation of moment about z is equals to 0. Also, the forces must satisfy the parallelogram of forces. Supposing we have two forces in the plane, one normal and the plane force in the direction of the plane, which is the form of a shear. This must satisfy the resultant should pass through the diagonal of the parallelogram. Or if we are talking about forces in or stresses in 3 dimension, if we look into this parallelepiped, the forces acting in the x direction or the stress acting in the x direction, the y direction and the z direction, the resultant of this must be acting through the diagonal of this parallelepiped, and this is the resulting stress of all these stress components. So, either in 2 dimensional plane this configuration or in 3 dimensional plane this particular configuration, which is the parallelogram of forces, must be satisfied. So, these are the two basic axioms based on which the forces which act on the deformable body are guided. Also, the mechanical properties of the material is essential to be satisfied. So, these properties of material are to be established through laboratory experiments. Hence, the equilibrium of forces and mechanical properties, these two are the main aspects of behavior of deformable member subjected to forces. Well, now having discussed about the questions which we had posed last time, now let us look into the aspects which we are going to cover in this particular lesson. Now, in this lesson we are going through the aspects of stresses in such a way that once this lesson is completed, one should be able to understand the concept of stress in a body, understand relevant stress components, then one should be able to understand why we need to go for the equations of equilibrium. For a given problem, one should be able to draw the free body diagram and evaluate the stress resultants from those diagrams and thereby compute the stresses. Well, if we define the scope of this particular lesson, as we have seen in general, the structural components are subjected to stresses due to external forces. Now, this particular lesson will help in evaluating stresses in structural components in a systematic manner. How do you go? How, if we are given a problem, how we draw the free body diagram of that particular problem, considering the external forces and the resistive forces that are acting on the member. And finally, once we know the stress resultants from the equations of equilibrium, we should be able to calculate the stresses at different sections as we desire. Well, the approach for analysis of external forces should be through the development of free body diagrams for evaluation of reactive and internal forces, and thereby the evaluation of developed stresses due to external forces. Well, in the last lesson, I had introduced this concept of stress, which is at a particular smaller element. If the intensity of force is acting, we had defined that force per smaller unit area as the stress. Now, this stress, when it is multiplied this is acted on by the external forces. If we take a small element in which a stress is acting, this stress multiplied by the area gives the force which we call as stress resultant, and the total stress resultant, that means the stress multiplied by the elemental area integrated over the whole of area, is the resulting force which we call as a stress resultant. And thereby we assume that at every point it has the same behavior. So, at any section, vector sum of the forces keeps the body in equilibrium, and that is how the stress resultant we obtain for that particular section. So, our job is to evaluate this stress resultant, and once we know the stress resultant, we can compute the stresses at that particular section. Well, we are interested to know the resultant stress vector at any particular section. Let us look into a body this is x axis, this is y axis, this is z axis. Let us take a body which is acted on by external forces. If we cut this particular body through a plane which is perpendicular to this, or rather parallel to yz plane, then the normal drawn on this particular plane will be parallel to x axis. As we had defined last time, for any plane, when we draw the normal to that particular plane, and if that particular normal coincides with any of these axes, we designate that plane with the name of that particular axis. For example, here we have cut this body through a plane which is parallel to yz plane. So, if we draw the normal onto this section, this normal is going to be the parallel to x axis, and thereby this particular plane we designate as x plane. Now, on this x plane we have at a particular point so a resulting stress which we call as R. Now, if we take the component of this stress R in 3 perpendicular axis direction, then we have a stress acting in the direction of x, which is normal to this particular section, and as per the definition of normal stress, this is the normal stress acting in the direction x. If we take the component of R along y axis or parallel to y axis, then in the plane we get a stress which is acting in the y direction. Also, we have a component which is acting in the z direction. The stress which is acting parallel to y or in the y direction, we designate this as the stress tau acting in the plane x in the direction y, which we call as tau xy. Or if we designate this particular stress which is acting in the plane x along z direction, so this we call as tau xz. So, thereby on this particular plane, on x plane, we have 3 stress components, which is one is the normal to the plane and other 2 are in the plane in the direction of y and z. The normal stress we call as sigma x, and other 2 components which are in the plane we call them as shearing stresses, and they are tau xy and tau xz. Likewise, if we cut this body with a plane which is parallel to this xz plane, we cut along this, on this plane on a particular point we can get 3 components of the stresses, and they are sigma y, tau on the y plane in the x direction tau yx, the shearing stress tau in the y plane in the z direction as tau yz. Also, if we cut this body with a plane which is perpendicular or which is parallel to xy plane, and if we plot the 3 stress components, the stress which is normal to the plane will give us the normal stress sigma z, and 2 stresses which are in the plane, they are on the z plane in the x direction and stress in the z plane in y direction. So, these are the 9 stress components that we are going to get at a particular point. Now, if this particular body is cut in such a way, we take another plane which is little away from this particular plane at an infinitesimal small distance away from here, and the slice we get, if we cut it off by 2 parallel planes, then we can get a small cubical element on which we can plot the stresses. So, stress at a point, thereby the 3 faces which are visible to us, which are in the front of the board, if we look into that, this particular plane, so let us say this is x axis, this is y axis, this is z axis. The stress on this particular plane, in the direction of x is the normal stress sigma x, this being the x plane, x plane, the stress acting in the y direction is tau x y, and on the x plane the stress acting in the z direction, we designate that as tau x z. Likewise, on this plane we will have stress acting in the y direction, the normal stress, which is sigma y. The positive direction of x on the y plane, we have the shearing stress, which is designated as tau y plane x direction, and on the y plane in the z direction we have the stress, which we designate as tau y z. This particular plane, the normal to which is parallel to z, we call that as z plane, and on this we have the stresses acting, the normal stress, which is sigma z. On the z plane in the x direction we have tau z x, and then this is the z plane. In the y direction we have, which is in this particular direction, positive direction of y. So, this is tau z y. Likewise, on the other three faces which are hidden from this side, this face and this face also have the three components of those stresses, which are sigma, tau, and in two planes we will have tau. Now, this particular plane, the normal to this, which is acting in the negative x direction, will have the stress sigma x acting in this particular direction, which is sigma x. The face will have the shearing stress component, this being the x plane. So, in the direction, opposite direction of y, we will have the shearing stress. So, this is tau, which is tau x y. In the x plane in the z direction, but opposite direction of positive z axis, we will have x z. So, this is tau x y and this is tau x z. Likewise, on the y plane, we will have the stress acting perpendicular to it, which is sigma y. The y plane in the x direction will have the shearing stress, but it will be on the opposite direction of x, this being the other end. On this y plane in the z direction, we will have stress which is tau y z. So, this is tau y x and this is tau y z. Likewise, the other side of the z plane, we will have the normal stress acting, which is sigma z, and on the z plane we have stresses the x direction, which is tau z x, and in the z plane we have tau z y. So, these are the stress components that will be acting on this particular body at a point. Now, let us look into the state of stress at a point. Now, as we have seen that state of stress at a point is represented by those 9 stress components. Now, 3 stress state, like they are represented by the 3 stress components like sigma x, tau x y, tau x z, likewise in other planes. So, all these 3 stress components are written on 3 mutually perpendicular axes, and they are represented by a term which we generally write as tau ij, which is called as the stress tensor. So, stress tensor is tau ij, where I represents the x, y, z directions or the x, y, z planes, and j represents the 3 stress directions. So, if we expand this on the x plane, when I is x, we have j as x y z. So, the stress components are tau x x, tau x y and tau x z. When I is the y plane, we will have three components in x, y and z direction. So, we have tau y x, tau y y, tau y z. Likewise, when I is the z plane, we will have three components in x, y and z direction. We have tau z x, tau z y and tau z z. Now, the components which are tau x x, tau y y and tau z z, they are being normal to the plane. We let us call them as sigma x, this as sigma y and this as sigma z. So, we have the stress component sigma x, tau x y, tau x z, which is acting on the x plane. We have tau y x, sigma y, tau y z, which is acting on the y plane, and tau z x, tau z y and sigma z, which are working or acting in the z plane. So, these are the 9 stress component we have at a point. Now, let us look into another aspect of it. Out of the stress components which we have obtained, now let us call this again as x axis as usual. We call this as y axis and this as z axis. Now, if we take the moment of all the forces, now let us assume that this distance which we have taken at a particular point in the body is dx, the vertical height being dy and along z direction the width being dz. Now, if we like to take the moment of all the forces about z axis, now in this particular figure only the forces which will have relevance while taking moment about z axis has been taken into account. Now, this particular plane being x plane and the force which is acting in the y direction, as per our nomenclature we call this as tau x y. Accordingly, this particular component of the stress which is acting in the direction of x and acting on y plane, we call this as y x. Likewise, this is also tau y x and this as tau x y. Along with this, we have the other stresses like normal stress sigma x, sigma y, sigma z and the shearing stress components as well in the other planes. Now, since only these forces or these stress components are going to cause the moment, other forces have not been shown over here. Now, if we take the moment of all the forces about z axis, then the moment expression can be written as tau y x is the stress acting on the area dx by dz. So, tau y x multiplied by dx multiplied by dz is the force. Moment about z axis is the distance dy. So, this multiplied by dy is the moment about z axis of tau y x, which is clockwise in nature, minus tau x y, which is acting on the area dz times dy. So, tau x y multiplied by dy multiplied by dz is the force, and if we take the moment of this force with respect to z axis, then this is multiplied by the distance dx. Now, assumingly that there are body force components in the x and y direction, which we say this x is the body force per unit volume, then along with this we have plus, well, for the time being, let us say the body force components we are neglecting, because that is also going to not cause any moment as such with respect to z axis. So, this we set equals to 0 for equilibrium. This produces a tau y x as equals to tau x y. In effect, this means that the cross shear terms, the tau x y and tau y x, they are equal. Likewise, if we take the moment of the forces about x and y axis and take the relevant forces, we can see that the tau z x is going to be equals to tau x z, and tau y z is going to be equals to tau z y. So, this gives us that the cross shearing terms, they are equal. So, if we look into the stress tensor which we had, tau I j is equals to the, if we write in a matrix form, we had sigma x tau x y tau x z, we had tau y x sigma y tau y z, we had tau z x tau z y and sigma z. So, this is the stress tensor. Now, from the equality of the shear, we have obtained that tau x y is equals to tau y x, we have obtained tau x z is equals to tau z x, we have obtained tau y z is equals to tau z y. Thereby, the stress tensor can be written as tau I j in matrix notation again as sigma x tau x y tau x z, y x and x y being the same, let me write this as tau x y sigma y and tau y z, z x x z being same, we write this as tau x z tau y z and sigma z. So, thereby it reduces to the 6 stress components sigma x, sigma y, sigma z and tau x y, tau x z, tau y z, and this we find is symmetrical in nature. So, the stress tensor has a symmetric form. Now, if we write down the stress components in a 2-dimensional plane, then the stresses we call as the elements in plane stress. Now, from the foregoing discussions, we know that the stress components which we will have here, they are sigma x, the normal stress, this being the x direction, this being the y direction, we have the stress sigma y. So, we are concentrating on the x y plane, and this is also sigma y, this as sigma x, and this being x plane acting, the stress acting in the y direction. So, we call this as tau x y. This being y plane and this here is acting in the x direction. So, according to our designation nomenclature, we call this as tau y x, but since tau y x is equals to tau x y, we call this as tau x y, and so are these stresses which are tau x y and tau x y. Now, since all the shearing stress components are tau x y, we can call these as say, tau, simply tau. So, we have stress normal stress component sigma x, sigma y and the shearing stress component tau. Now, having known the stress at a particular point which is acting, which are the combinations of normal stresses and the shearing stresses, let us look into that if we have a body and if we are interested to find out the change in stress from one point to the another, then to evaluate the stresses or to the change of the stresses from point to point, we need the equations, certain equations to be solved, and those equations we call as equations of equilibrium. Coming back to this body here, say for example, we have a body which is stressed and we like to find out the stress, change in stress from this point to this point. So, we need these changes to be evaluated through these equations of equilibrium. Now, as usual, we call this axis as x axis, this as y axis and this as z axis. Now, on this particular plane, which normal to which is parallel to x, which we have x plane, we have the stresses which is normal stress sigma x. We have the two shearing stress components, the x plane acting in the y direction, which we call as tau x y, we have stress in the x plane in the z direction, which we call as tau x z. Now, when it comes to this particular plane, which is at a distance of dx from this plane, and likewise let us assume that this length is dy and this is dz. So, the stress which will be acting in this, the normal stress, will have component as sigma x will have component as sigma x plus del sigma x del x, which is acting over the length dx. Likewise, we will have the shearing stress component tau x y, which is varying from this end to this end, will have tau x y plus del tau x y del x over the length dx. We will have x, the z direction, tau x z, which is tau x z is on this particular plane. So, when it is coming to this plane, there is a change over the length dx. So, tau x z plus del tau x z del x over length dx. Likewise, the stress on this particular plane normal to this, which is a y plane, will have sigma y. The forces, the stress which will be acting normal to this is sigma y plus del sigma y del y over the length dy. The shearing stress component on y plane acting in the direction of x will have tau y x plus del tau y x del y over length of dy. On this plane we will have sigma z, and the normal stress on the front z plane is sigma z plus del sigma z del z over length dz, and so on. Now, if we take the forces which are acting in the x direction and sum them up, so as per the equations of equilibrium, the summation of all the forces in the x direction must be equals to 0. So, if we write down the forces in the x direction, we have sigma x plus del sigma x del x over dx So, the equations we have sigma x plus del sigma x del x over dx and acting over the area of dy times dz. Minus sigma x acting over the area dy dz. Also, in this particular direction we have plus tau y x plus del tau y x del x times dx del tau y x by del y times dy acting over the area dx and dz minus tau y x dx dz plus we have the term on the z plane acting in the x direction, which is tau z x plus del tau z x del z over dz multiplied with the area dx and dy minus tau z x times dx dy plus if we assume that x is the body force per unit volume, so this multiplied by dx dy dz is set equals to 0. So, from this we will get del sigma x del sigma x del x. If we cancel out these terms, and divide the whole equation by dx dy dz, we have del sigma x del x plus del tau y x by del y plus del tau x z by del z plus x is equals to 0, where x is the component of the body force. Likewise, if we take the equilibrium of the forces which are acting in the y and z direction, we get another two sets of equations, and they are del tau x y del x plus del sigma y del y plus del y z del z plus y is the body force component equals to 0, and del tau x z del z, I am sorry, del x plus del tau y z del y plus del sigma z del z plus z, this is equals to 0. So, these are called as the equations of equilibrium. Now, these equations of equilibrium can be written down in a two dimensional form as well, and if as usual if we designate these is in x y plane, here we have x, here we have y, this is sigma x, this is sigma x, and the variation along the x as sigma x plus del sigma x del x over the length dx, where this is length dx and this is dy. This is tau x y, and this is tau x y plus del tau x y del x over the length dx. This is sigma y, this is sigma y plus del sigma y del y over the length dy. Then we have tau, this is tau y x, and this gives the variation of tau, which is tau y x plus del tau y x del y times dy. So, these are the stresses in two dimensional plane, and if we take the equilibrium of the forces in the x direction, then we can obtain the equations of equilibrium in two dimensional plane, which could be del sigma x del x plus del tau y x and x y being same, we can write this as tau x y del y plus the component of body force x, this is equals to 0, and likewise the other equation will be del tau x y del x plus del sigma y del y plus y is equals to 0. So, these are the equations of equilibrium in two dimensional plane. Now, having known these stresses at a point, equations of equilibrium, and how to evaluate those stresses or how to write down the stresses at different planes, let us look into that if we have to evaluate the stress in an axially loaded member. That means, we have a member, we have a body in which we have the force which is acting is in the axial direction. Let us call this body is acted on by the force P. Now, if we like to evaluate the stresses at any inclined plane, let us cart this body by an inclined plane. And if we draw the free body diagram of this, then we have the body in this form. Now, here we have the resistive force P which is acting on this. The resulting force or the stress resultant will be acting in this particular direction to equilibrate the body. Now, we can take the components of this force in the normal direction, normal to this plane, and along the plane, which will give you the three force or the stress components, which is normal, which we call as the stress corresponding to the normal direction as the normal stress, and the two shearing stress components tau. If we concentrate on the two dimensional plane, if we take the axially loaded member, the member is subjected to the load P in the axial direction. Let us take a plane which is cutting this body in this form, and let us assume that this plane is making an angle of theta with the vertical. If we take the free body diagram of this particular body, this is angle theta, we have the force acting here as P. The resistive force acting to this body to keep in equilibrium is P. So, this will have two components, one along the normal and one along the plane of this particular section. Now, this angle being theta, if we drop a perpendicular here, this angle also is theta, hence this particular angle also is theta. So, the force component along this is P cos theta, the force component along this is P sin theta. Now, if we say that the cross sectional area here is A and the cross sectional area of this as A dashed, then the stress which is acting in this particular inclined plane, if we say the normal stress sigma theta, theta being designated by this particular plane which is cut an angle of theta with respect to the vertical, sigma theta is equals to the normal force component which is P cos theta divided by this area A dashed, and A dashed from geometrical property here we can say A dashed is equals to A by cos theta. So, P cos theta by A cos theta, A by cos theta. So, this leads to as equals to P by A cos square theta, and the stress which is acting in the plane which is P sin theta, the stress, the tau theta is equals to P sin theta divided by A by cos theta. So, this eventually is going to give us p by twice a sin 2 theta. So, these are the two stress components on this inclined plane. The normal stress is p by a cos square theta, and the stress which is parallel to the plane, which is shearing component, is p by twice a sin 2 theta. So, the maximum values of these, maximum value of sigma theta is when cos square theta is equals to 1, leads theta is equals to 0. And for this sin 2 theta as 90 degree, 2 theta as 90 degree. So, theta being 45 degree is the maximum value of the shearing stress. So, maximum value of the normal stress is p by a, and maximum value of the shearing stress is p by twice a. So, eventually the relationship between sigma theta and tau theta, we can say that tau theta is half of sigma theta. Tau theta is equals to half of sigma theta. Well, then we have seen the maximum normal stress is p by a and maximum shearing stress is p by twice a. Shear stresses are that this particular body is acted on by the force P. Eventually, the resistive force will be in this as p by 2 and p by 2. At this level, if we take the free body of this part, if I cut here, then this particular body will have p by 2, and this also is going to be resistive as p by 2. So, at this particular section, this is p by 2, this resistive is going to be p by 2. Now, here, well, there is little amount of eccentricity for this force to be transferred over here, and this we ignore, this being the thickness being smaller, and this p by 2 is called as the shearing force, and shearing force divided by this area which is acted on between these two plates is called as the shearing stress. So, if we say this width is b, this width is t, then the shearing stress is p by 2 divided by b times t. This is going to be equals to tau. Now, here we have given a problem where two plates are connected by two bolts, for which we will have to evaluate the normal stress, shear stress and the bearing stress. Well, we will solve this particular problem in the next lesson, and we will demonstrate. Meanwhile, you can work on this particular problem, and we will give the solution of this in the next lesson. Thank you.